free energy change inside is going to be debited because I moved it out, and the free energy on the outside is going to be positive. And so if I look at the total change in this whole system, it has to be equal to zero. Okay? And so if the system is in equilibrium, in other words, if it's not changing, if the implication here is that if J in and J out are equal, the flow rates are equal, then the concentration outside and the concentration inside is going to be constant. This is not the typical case. Okay, I want to point that out. But for the mind game that we're playing here now, I'm going to assume that these two flow rates are exactly equal. If they're exactly equal, it doesn't mean that the concentrations are equal. It just means that the concentrations are not changing. Right? And so, anyway, basically, if you look at equilibrium, if the total change in free energy when I do this experiment is zero, then basically the concentrations stay the same. If it's less than zero, then the free energy inside is greater than outside, and the process is spontaneous. If it's greater than zero, then energy is required to make it happen. Okay. So if you follow this through, basically at equilibrium, these are called equilibrium potentials. Delta G equals zero at equilibrium. That implies that the molar free energies have to be equal, and the molar free energies being equal reduces right back to our Nernst equation, which by now I'm sure y'all all got memorized. So anyway, basically you get kind of reassuring that we get basically the same equation. Okay, any question about this little experiment? Yes?
Should we know how to derive all these equations?
No, you don't have to know. Just kind of memorize the Nernst equation.
Okay.
So without proving it to you, the more general equation is this equation right here. Okay, I'm not going to prove it in this class. It can be proven, but this is called the Euston-Terrell independence equation. And basically it says that the ratio of the flow rates in and out is proportional to the ratio of the concentration inside and out times E to the ZF Bm over RT. And so this is the equation that actually governs a system not in equilibrium now with concentrations that are changing inside and outside of the cell. You don't have to memorize this equation, but I'm just kind of showing you that there are certain cases where, if the flow rates turn out to be equal, then the natural log of 1 is 0, and mu out and mu I are equal, and you basically get back to the Nernst equation again. Okay? And so this is a very important equation for actually calculating the energy expenditure that the cell does in order to hold things in certain equilibrium. Okay, so we actually use this to determine how much work that the cell is doing and can apply that. And you can kind of move things around. It turns out that the metabolic energy that's required to hold something in a non-equilibrium state is the universal gas constant times the temperature in degrees Kelvin times the natural log of your flow rates ratio that you measured divided by the flow rates that you would have expected had it been in electrochemical equilibrium. And so again, it's not hard to see this, but the natural log of 1 is, if those two things are equal, Ji over J0, and out are the same. Measure the passage of that ratio. If that's 1, what's the natural log of 1? 0. And so if that's 0, that means the amount of metabolic energy that you expend is 0. Okay? So if what you measure is what you expected in electrochemical equilibrium, if the equilibrium implies it's not changing, then basically it doesn't take any energy to have those flow rates. Right? So it's kind of reassuring. You basically kind of go back to the same thing. All right? Any questions? Here's some examples. Here's a cell. We have some weird Martian cell maybe. It has concentrations given here. So basically, what we're doing here is we're saying C inside for the sodium chloride is equal to C outside. So the concentrations here are the same, okay? But we're measuring with our fluorometer. We're actually measuring some different flow rates. And so we can put these flow rates down, and we can put these into our wonderful equation. And so in this case, we measure the flow rate in over flow rate out. Okay, if we do that, it's 110 over 0.1 or 11. And theoretically passive, because we also measured the membrane potential, we would have expected this to be 0.062. Okay? Now, these two are not equal. Okay? Because those two are not equal, that implies that the cell is probably actively pumping something. And if we kill the cell, and if we measure these fluxes go to zero, in other words, these all change to zero, that proves that we have some active transport phenomenon occurring. And that's for sodium, so that's the ratio of sodium. If we look at the flow rates for chloride ion, we measure this ratio as being the 259 over 156. And that gives us 16, and chloride was passively distributed, again, using the Nernst equation we just had. It turns out that we get the same number. So this is within our experimental error bar here. These are the same. And whenever they're the same, we don't have to kill the cell, but you can assume that it's passively distributed. And that's how we can tell that chloride is passively distributed. Yes?
For the equation in that bracket A, where it says 10 raised to the negative 70 over 58, is that the same thing as when you changed it earlier to log from natural log?
Yeah, this is the same equation. Yeah, that's this is what you actually measure. So I've given you this as a part of the problem. Okay, but when I go back to the Using Terrell, in the Pim's equation, one I did not prove to you, okay, I look at these C inside and C outside C, they're the same. So this is 1, 10, so basically that's 1, 10 to the minus 70 over 58. And you basically add this in here, you come up with 0.062. So this number is not equal to what you would have expected had it been in passive distribution. And that tells you that it's probably active. Okay, you don't know for sure until you kill the cell, but you poison it with something, and you see the flow rates change. That then absolutely proves that it's not being passively distributed. To prove passive distribution, all you have to do is to prove that whatever you calculate in terms of your flow rates and concentrations, they're equal to what you expected. Okay. Yes?
So how do we go from the E in the Using Terrell equation? Like in the equation on the previous slide, it was an E to the...
This one? This one?
Yeah, that one. So it's E to the C, or at that. So how did E become that? Was there some like...
How do I go from natural logs to base 10 logs? Is that your question? I mean, right here.
I guess, yeah.
Base 10 log.
So you say...
Yeah, that's a good question. Not real sure about that.
I think it's the same way you simplified it earlier.
Yeah, okay, look, okay, it's the same way I did earlier, because I've got 58 here, okay? So I've basically gone back, see, I've got 70 millivolts, and here's 58, okay? So I've basically done that RT over ZF, the room temperature, and I've converted already to base 10 logs. Okay, that's exactly right. Thank you, whoever saw that. Any other questions? Okay. So here's another example. This is a muscle cell. This is some weird Martian thing. I don't know what that is. But anyway, here's a muscle cell. And this has the potassium, chloride, and sodium, about what we would expect inside the muscle cell. A fair amount of potassium, not much sodium. And then outside we don't have much potassium. We have a whole bunch of sodium. Okay. And we also measure the membrane potential to be 90 millivolts. And again, be careful here. I point out to you that I have defined this just to be, again, kind of different. I've defined it different than your book would define it, because your book usually defines it on PM minus V out. But anyway, it makes no difference. if you kind of go through, you have to do each ion at a time. So basically, you look at potassium, 155 and 4.5. Okay, if you put these concentrations in voltage to 20 millivolts, it turns out that what you would expect is exactly what you measured. It's about 90 millivolts. So probably, we're looking at a passive distribution. The chloride ion, again, put the ratios in, convert it over to the natural logs, the log base 10, calculate about 91 millivolts, and that's about what we measured. So it's probably passive too. Sodium's way different. Sodium, if you do the numbers here, and it turns out that you would expect that number would have been a minus 57 instead of a positive 90 millivolts. You kill the cell, you can prove that it's actively distributed. So that's the way that you kind of go through. Now, if you can go even farther here, you can actually look at, remember I told you to calculate how much energy the cell is actually expending. And so you have, this is kind of what you would expect in electrochemical equilibrium, and this is the excess metabolic energy that is being expended. So if you go through and put these numbers in, if you go through this, it turns out that you're expending 14,343 joules per mole of sodium ion transport. So it takes that much energy to hold that sodium out of its electrochemical equilibrium. Huge energy expenditure. It's the vast majority of your growth cycle and glycolysis is converted to, is actually being focused in on maintaining this energy requirement to keep sodium out of its equilibrium potential. You can also go through and calculate out the work rate. So work rate would be per unit area of the cell, and it basically turns out to be about 143 joules per kilogram hour per unit area. And so again, a very, very high work rate. Your cell is expending an incredible amount of work in order to keep the sodium ion in the distribution that I gave you in that this example. This is actually a realistic example. Any questions? Okay, y'all have enough for today? Okay, we'll start from here next time.